I'm going to start with a bit of a view on the practical side of NMR, and then continue with setting up the stage on how to transform the chemical NMR problem into something that can be addressed via spin physics. So, that is what an NMR spectrometer looks like. The way it works is you take a sample and insert it, and in the spectrometer it is subjected to a very strong magnetic field. And it makes, like typically the sample is diamagnetic, it has to be, and the nuclei align with the static magnetic field. And then you apply pulses in perpendicular direction to the static magnetic field, which need to be in resonance with the energy required to flip the spins. And after applying the pulses, you measure the response. And what is special about NMR, or what makes it useful, is that the response frequency of each nucleus differs a tiny bit on its chemical environment, and that makes it enormously useful for chemistry. So in organic chemistry, NMR is the go-to tool that gives you information on chemical structure. So this example molecule is artemisinin. It's extremely important in the context of malarial medication. And of course, if you want to find out what the structure is, if you want to know, okay, is maybe some detail about the molecule actually different? Is it really the same thing that you're seeing here, or is the structure maybe a bit different? The way you confirm it is with different types of spectroscopy, but NMR spectroscopy is the most important one. And one of the strengths is actually that you can address different nuclei. So you can address different isotopes. Most commonly it would be protons, but you can also address carbon-13, a bit less commonly fluorine, phosphorus, boron, and so on. But also, because you're applying pulses, you can employ different pulse sequences, and that means, in fact, you have one device, but you have tens, even hundreds of possible experiments that you can perform, and a smaller one of those are performed routinely. So in this case, this is artemisinin with its proton NMR spectrum from the BMRB database, biological magnetic resonance database. And and does it switch? Yes, as I said before, the proton NMR spectrum is just one example, but in fact, if you just take this one molecule and the one spectrometer, you can perform a wide range of different experiments. So you can acquire proton NMR spectra, you can acquire broadband decoupled carbon NMR spectra, you can perform all types of 2D NMR spectroscopy that give you a wide variety of information on the chemical structure of the molecule that you couldn't acquire with other techniques, maybe with the exception of X-rays, crystallography. Now, what is to be said about the instrumentation? Well, NMR is extremely versatile, but it comes at a cost. So, like an NMR spectrometer has a superconducting magnet, for which you need liquid nitrogen and liquid helium, and any sufficiently well-funded chemistry department is going to have NMR spectrometers. Bigger companies will have their own interval service departments. Smaller companies will have to send their samples to dedicated service providers. So the instrumentation is certainly a hurdle in applying NMR. Like during the past, let's say 20 years, so-called benchtop NMR devices have been developed, which employ permanent magnets. And in contrast to these big machines that fill an entire room, like a benchtop NMR spectrometer has more like the size of a printer and the weight of a washing machine. So you can, even a not so big company can afford to buy one of these devices. It comes, however, at a cost. So there is lower sensitivity, there is lower resolution. And if you look at the spectra, you simply don't get all the sort of fine structure, especially in more complicated cases, that you get at a high field machine. So if you're a chemist who performs structural elucidation, you may prefer to have the spectrum that is at the top. But if this is just too costly to acquire, then maybe you will be happy with the one at the bottom. It's actually a bit of an irony of the history, because the earlier NMR spectrometers, they used to have first electromagnets, then permanent magnets, and then they development went towards superconducting magnets. But for some applications, you may actually want to go back to permanent magnets, and that's the development of magnetic materials that permitted benchtop NMR spectrometers to be constructed nowadays, as opposed to still these extremely big machines you used to have many decades ago that employed permanent magnets that needed to be much, much larger than they are nowadays. And if you want to simulate what the spectra look like at different frequencies, of course they depend on the frequency, you can just go to the HQS website, HQS Spectrum, and try it out for different molecules.
Maybe we should tell people that the frequency that you out here is so the magnetic field strength and the frequency
yes.
have a one-to-one correspondence.
Yes. Like in R&D or in R&D adjacent areas, like it's clear NMR is extremely important, but what about other areas that are a bit closer to production, that are closer to other applications, such as in biology and medicine? There, I would say NMR has a much more difficult game to play, because on the one hand, yes, the spectra contain extremely rich information. They are also very robust and reproducible, but one challenge certainly is the instrumentation. So if you have such a complicated device that you need to put somewhere, in many institutions that's not even available. So that is however, something that can at least to some extent be addressed with benchtop NMR spectrometers. Another intrinsic complication of NMR is sensitivity. So mass spectrometry, for example, but also different other types of spectroscopy are much more sensitive towards lower concentrations. So for NMR, you need a bit more sample. And finally, especially if you go to benchtop devices, but also at high fields, analyzing samples, but especially if you are actually working more in quality control in biology and you have samples that are mixtures of compounds, analyzing such samples is anything but straightforward, and this is actually something which you can address quite well with software, in fact, where you have to employ software and simulation techniques in order to get the most out of the instrumentation. So that means we can now move to something that starts looking a bit less like chemistry and a bit more like physics. So let's say we want to simulate the NMR problem. How do we do that? So what we need to start with is to define the spin Hamiltonian. And luckily, NMR is a problem which is extremely well described by such a relatively simple spin Hamiltonian. So what we have here are the capital I's, which are placeholders for the nuclear spin operators. And in fact, if you are interested in quantum computing, which most of the people present here probably are, then you can also realize that at least for spin 1/2 nuclei, the capital I's are 1/2 the Pauli operator. And all the complicated interaction that the nuclei have with their chemical environment molecule is absorbed into the parameters of the spin Hamiltonian, which I'm going to explain in a bit more detail now. Also, it's important to point out that it is for diamagnetic molecules in non-viscous liquids, or for solids or for proteins. It may look a bit more complicated, but this actually covers the majority of application cases of NMR in chemistry. So the first term is the Zeeman term, which describes the interaction with the static magnetic field. And as Michael said, this is the point where the magnetic field enters. So what we have is, on the one hand, the gyromagnetic ratio, which is specific to a given isotope. And the other parameter that enters is the chemical shift. The reason we have this is because nuclei are diamagnetically shielded in a sample. And the shielding is a bit different depending from molecule to molecule and from atomic position to atomic position in a molecule. So this example is isoprene that you see at the bottom, and what you see is that the protons in the methyl group, so that's the one with the CH3 group, they have a value of about 1.85. The terminal CH2 groups, they have chemical shifts of about 5. The one in the middle has about 6.5, and these tend to be pretty characteristic of the specific chemical environment. The second term that we have describes the interaction. We don't have direct through space dipole interaction between the spins because it averages out due to a very fast rotation of the molecule in solution. What we do have, however, is coupling that is transmitted through the bonds indirectly. So there is the so-called J coupling, and that provides us with another extremely important piece of information on the structure of the molecule. Here you see a few example values for the isoprene molecule, at least for part of it. Now let's proceed. So how would we go about actually determining these parameters? So what you see here is an experimental spectrum of propofol, which is very important for general anesthesia. So if you've ever been in hospital and received surgery and had general anesthesia, chances are that you were injected propofol. That is what its spectrum looked like if you record it on an NMR machine. And like typically you all need to magnify sections of that. I would even magnify them a bit more if I didn't want to pack everything on one slide. So you see the spectrum of the molecule itself. You also see a bit of moisture, which is the water peak. You see DMSO, so that is in fact deuterated dimethyl sulfoxide, which is the solvent. So you see traces of protonated solvent molecules in there, and the remaining peaks are due to different parts of the molecule. Okay, so this is a spectrum, and now how do we determine the parameters if you want to simulate this on a computer? So there are a few approaches. One of them is to say, okay, like you've got the experimental spectrum, you can determine the parameters from the spectrum. If you want to go about it rigorously, you can try to fit them. That may work out. It may sometimes not work out. It can also converge to a wrong solution, but this would in principle give you very accurate parameters. If you have a relatively simple spectrum such as propofol, you could also just go ahead, measure the positions of the multiplets, measure the distances between the peaks, and at least get an estimate of the parameters. That would work even worse for complicated molecules. But that of course requires you to be able to do the fitting procedure in the first place, and like this works if you have a sample and you know precisely what is in the sample. A lot of the time you want to do structural sedation, so like you want to know, okay, do I actually have what I think is in the sample or not? In that case, you would probably want to predict the parameters. Broadly speaking, we have two approaches for them. One is to employ quantum chemistry. So that is generally applicable, but it's quite complicated. So this is something that we're working on. And the other stream of approaches would be to employ empirical methods or data-driven methods, for which you certainly need input data that is reasonably similar to the data that you're trying to predict. And as any data-driven approaches, they are prone to the garbage in, garbage out problem. It's also something that we're working on, hopefully without the garbage. Okay, so let's look at approaching it from the quantum chemistry viewpoint. So this is propofol. So the way chemists draw propofol is like what you see to the right. So first of all, we need to obtain the 3D positions. So that is something that we do with one of the standard chemoinformatics tools. Then we determine the precise atomic positions in space. So that is done with the so-called geometry optimization. Then we go ahead and deploy density functional theory, and a few codes, one of which we license, is capable of computing NMR parameters. So we calculate the shieldings, we calculate the J coupling constants, and then we determine the final parameters that you can actually measure in experiment. So this comes with a cautionary warning that maybe this isn't something that you should do normally. The reason why is something that you can see here. So at the bottom you see the experimental spectrum. At the top you see the predicted spectrum. So first the predicted parameters, and the predicted parameters are used to simulate the spectrum with the HQS tool. And that is the result is really, really bad. The reason isn't density functional theory, for those who might assume. The reason is completely different. The reason is that you're not actually describing the right problem, because most organic molecules have conformational flexibility, meaning that they can rotate especially around the single bonds, and NMR timescales are pretty long. So on the NMR timescale, each molecule visits many different conformations, and like the effective spin Hamiltonian is most adequately described as a time average. So if you want to model the problem adequately, you need not only to generate one structure, but you need to generate all the accessible structures and average the parameters thermodynamically. So this is what we do. So we have developed a workflow which uses the standard tool for conformer search. It optimizes the geometries of all the conformers, determines their energies, determines their NMR parameters, and so on. And of course, makes use of standard components. Yet setting up this entire workflow is a pretty complicated undertaking. So we've been working on that for about 2 years, and now we are getting pretty good results. Then you actually get parameters that are realistic, as you will see. And an important component of our approach is actually the completion of degenerate structures, because you have different conformations. And for a simple molecule like propofol, you may not expect it, but like each conformer is actually 162-fold degenerate. And this is actually something that the state-of-the-art standard conformer generators, they don't get it. Like this is actually a very important component in our approach, and one for which we have submitted patent applications, and you will see why. So let's say, first of all, this is if you leave out this rotor completion components, now you get results which are much, much better than you saw a few slides ago. So the positions of the multiplets are where they're supposed to be, but like the multiplets don't look at all like they should be. So let's say at round 3, you're supposed to see 7 lines, a septet. It doesn't look at all like that. The same goes for the doublet to the right. Like the shapes of the multiplets that are described by the interaction between the spins, they're completely wrong. Now, if you apply this rotor completion, which is this additional step, the results look much, much better. So this describes, let's say, more or less the state of the art in published literature, but this is what we get with our approach. So I can switch back and forth. Like you see, the positions of the multiplets, they're basically more or less on the spot already, so you can't get much better with DFT, but the shapes of the multiplets improve dramatically. Only though the one to the right still has some artifacts, so it's just superimposed doublets, but it looks much, much better than before. So this is so far so good. So this is what you can achieve if you employ a good workflow that makes use of DFT. But maybe sometimes you don't want to go through all the complexities, so you can maybe you want to use data-driven methods, and what we are developing are graph-based empirical prediction techniques. So let's say you build a database that contains NMR parameters for many, many molecules, and we are in the process of building up a database containing parameters for thousands of molecules that we will be able to use for this approach. And now what we're using for the prediction is not even machine learning. What we're doing is much simpler. So we say, okay, we have this molecule, propofol to the right, and then in the database, it doesn't contain the molecule itself, but it has many molecules that are kind of similar. So we can look up molecules where for each nucleus or for each pair of nuclei, we have a similar fragment, and we just pick the values from those molecules. And we can do that because NMR parameters are fairly local properties. So if you have a molecule and part of it looks similar, then maybe other parts that are far away from it don't matter to you so much, and we can actually get pretty good results with that. So you can go ahead, run the empirical parameter prediction, and this is what we get with a development version. So I would say for most nuclei, the results are actually not much worse than with DFT. Of course, you're always going to have to be off for some values. The only bit that's a bit off is, let's say, this at around 7.4, which ought to be at around 6.8. So there you have swapped the multiplets. Otherwise, I would say the approach is already doing quite well despite its simplicity. Plus, it is systematically improvable via extending the amount of information that you put into the empirical prediction database. Unlike DFT, this works in a matter of seconds, but in order to be able to make use of that, you need to build a custom database of parameters first. So to summarize, this is the approach that HQS uses to transform to quantum. Of course, quantum in quotation marks, because NMR in it by itself is an intrinsically quantum mechanical problem. So one thing you can use already is like if you can, like we have the so-called HQS NMR parameters module in HQ stage, which currently contains data for around 100 molecules that we have collected, plus more than 1,000 molecules from the so-called Gizmo database, which is on the biological magnetic resonance database, which contains parameters fitted to experimental spectra. Of course, with the database, the caveat applies that sometimes the procedure may converge to the wrong to a wrong assignment. This is actually something that I found quite by coincidence when I was getting the data for the isoprene molecule. So that was the one I was showing you on the slides with the spin Hamiltonian. In fact, it converged to the right numbers, but it assigned them to the wrong nuclei. So anyway, there are 1,000 experimentally determined parameters. There are about 100 molecules, which we have curated very carefully. You can use all of them. What is our default workflow for parameter prediction is we employ DFT and conformer sampling. And at the moment, this works in such a way that a customer, for example, would give us a list of many molecules for which they need parameters. We can go ahead, run the workflow, and give them the complete sets of shifts and J couplings that they can use for simulations on different devices with different magnetic fields where the spectra look differently. Also, what we currently have in development and which will be available via our web front end HQ Spectrum is an empirical prediction approach where you can just draw a molecule, get the parameters in a matter of seconds, and simulate spectra. And of course, finally, you'll see that a lot of the time the multiplets are about right. You just need to shift the positions a bit, and like this isn't really my topic, but like HQ Spectrum also has tooling to adjust the estimated parameters in order to fit an experimental spectrum, and then you can actually get pretty good results that apply across an entire range of instrumentation, whether it is benchtop spectrometers, whether it is superconducting high field NMR spectrometers. You can simulate the spectra throughout different conditions. So that's it from my side. Thank you for your attention, and now I think we have ample time for questions.